So we only left one course project. The task is the check it. Record. Oh, yeah, already record. Yes, we only left one subtask is we need to develop a program for the AWGN, a adaptive white Gaussian noise channel simulation with our specific modulation type and code worthiness. And we need to simulate two cases. First one is the without Hamming error correction code, and the second one is the with the Hamming code correction. And we need to obtain the BER codes for each case in the synchronous ratio range from the 0 decimal to the 15 decimal with step of the 0.5 decimal. And for uncoded the simulation mark, theoretical value calculated in the task 4B, which is the task 4B, we got this bit error rate for the specific signal-noise ratio and modulation type, and we need to make some conclusion of the use the code efficiency. So the idea is we need to have our binary data, and we need to design the transmit the signal, which must combined with the carrier frequency and your specific the modulation types, and we need some add the noise, and we will submit to the no, we have to transmit this signal, and we will receive this signal, and we will do correlator receiver, and we will compare with the different with sync noise range from 0 decimal to the 15 decimal, and we will compare their difference with the how do you say, we will compare their performance of the with the error correction code or without any error correction code, and we still have to compare with some specific error property with some in the task 4B iterate error for the specific signal ratio and the modulation type, and so this is the basic idea, and we need to use our individual parameters, and this is previous year's course project paper, and we don't have name, and you will have your individual parameters, and we can see here we have some symbols durations and signal to noise ratio in the task 4, right? So here we have the task 4B with the specific the signal noise ratio, and we need to calculate the bit error rate. So this is for the task 4B, and we need some error correction code. You have the group code or cyclic code, and your code worthiness, and the carrier frequency, and the modulation type, and if you have the frequency index and your phase shift, phase shift, both of them are same with the pi. And this is for your individual work. And for my case, I will use Dr. Anna's case where we will do the both of the frequency shift, both of the different modulation types. And let's do it. Firstly, close this one, and so we need some information, and each time we clear everything, we not need it. And the first is cross-project parameters. Let's save it as the task 6. And for the first one is the symbol duration. And you will notice here is nanoseconds. The TS. The case is 60 and 60 minus 9 will be the symbol duration for the second. Convert to nanoseconds to the second. And we have the carrier frequency. Carrier frequency is 2 gigahertz. 9 gigahertz to the hertz. And we need to the specific signal to noise ratio of no. Firstly, we need the signal to noise ratio range, not the specific signal to noise ratio. So for the ranges will be the 0 decimal to 15 decimal. We start with the 0.5, 0.5 to the 15. This R will be the dB. And for the frequency, index. And we need to binary data or transmit data. We need to generate it. Randomly. And so how many data do we need? And in this case, we think we hope there are numerous data, so we will consider as 1 million. 1 million data, but you know it will run very slowly. So I just to decrease the amount, and you will set it as the 1 million. I just set as the 10,000. So in your case, you have to set as 1 million, and I hope that it will run the bits to be sent. and we will generate the binary data with the arbitrary with the 0 or 1, and we use the randy function. Only can generate with the 2 or 1, and we have to minus 1, then we can get we wanted 0 or 1. The data signal with the row vector and with the n. We use yes, as I mentioned, I used the 10,000, and in your case you have to use the 1 million. So just with the 5 to the 6. Okay, and we need to next step we have to generate the carrier signal. And the samples per symbol 200. That will be the uh, yeah. Per symbol, and we need tau, which is the uh, symbol duration divided by the length, the number of the sample per symbol, and it is the time step, and we have to the interval, the time interval for the one symbol. It is will be the t. 0 to the step is dt. Uh, to the symbol duration minus the and we have carrier signal with the 2 multiplied with the pi frequency with this is the carrier signal, and we have the we can generate the each symbol's energy, so we don't have to skip to left it. Energy is very easy to just sum the carrier symbol square. Two. We use the dot multiplication, and this is will be the energy for and we need the synchronous ratio in the specific course project part, which is in my case, which is 12 synchronous ratio. We'll use the task 4B. audio. Is 12. And we need some two frequency and two energy for the frequency shift key keys. So it will be only for the binary frequency shift key. Will be the index mode divided by the, this is the index divided by the 2 multiplied with the symbol duration. We have two frequency. F1 will be the F0. Divided by, and next one is 2. We have both band, and we will do the frequency to carrier signal, and will be the S1 and S2 is different frequency. And for the energy of the symbol, we just separate as the EB2. Because for the both different frequency shift key case, their energy they are same. So we only need one is enough. This is for the frequency needed parameters, and we can do the modulation. And we have the transmit signal. Use the chronic multiplication binary data, carrier frequency. This is for the XK, and we need to have the 3 for B FSK and BPSK, and you only need one is enough. And for text 1, text 2, text 3, S1, and multiplied with the chronic. And mention here for the binary data, we need the inverse it for the, especially for the frequency shift case. And here is we have to do the convert to the Z here -2 +1, and this is for base shift key. And next step, we have to generate noise power. And the energy of the noise EB will be is 10 dot with the divide by the 10. Here we use the, I think the noise range is the single noise range, not the specific single noise in the course project. So here we have to notice, and this is the and for the noise power, it will be N0. The B noise power, that's it. And for the sigma is square T. We only use the score of the standard deviation of the noise. Sigma. And for the case we for the frequency shift case, we have to generate two different noise power, right? Because we have the different frequency. We have different frequency, and F1, F2 they have same energy, and F0 it has different frequency energy. It has different frequency, so it carry a single has different energy, and we have to generate the ratio for the frequency shift keying case. I just renamed as N2 EB2 divided by the noise ratio and the sigma 2. And so here we need to do some for loop, because we have the multiple, we have single noise ratio range, and we hope to get the of the point single noise ratio which had the result. It has uh, BER. So we have 15 number, we have 50 different single noise ratio with the step with the 0.5, which means we have totally we have the 30 samples. So let's do it. And with the for loop, okay, to the 1 single and sigma k. which is the sigma here, standard deviation of the noise, and we have get some the index here, and multiplies with the random random with the one, and then multiplied with uh, L is the number of samples and N is the number of the bits to be sent. So this will be the noise in the AWGN function. And we need to, for my case, we need to different noise because we have different sigma. And you don't need this one, you only need one is enough. And for the we have to so the noise is generated down, and we need to add it to the transmitted signal, and we can get the received signal. Transmitted signal plus the noise in the transmitted channel. So, and for the received signal, this is for the binary amplitude shift gain, and for the frequency we have different uh, transmit signal and different noise, especially different. And for the phase shifting case, we have the different transmit signal, but noise will be the same. So this will be FSK. And we need to perform the correlator, the receiver of the noise signal. And the next step will receiver of the noise. And here we need to use the reshape function, and it's already introduced in the lecture. And we reshape the single vector received signal with some matrix, and it will follow some names of the symbols and the samples per symbol, and so this is what we did here, and basically it's same. We just reshaped it, nothing changed. So let's do it, and the received matrix. So will be the received from the change the from the received signal to the received matrix. X will be the matrix, will be the reshape it. And for the, in our case, we have L, and L is the number of the samples per symbol, and n is the number of the bits. So it will be we just slice the receive the signal into segments. Segments. No, see, let's receive. Into column. And this is for the binary amplitude. Also, and you only need one because you only have one modulation tab. For the, this will be and here we have the 2, 3, and this will be the 2. This is for the BFSK and the BPSK. So, and the next step we have to do some demodulator, which is the demodulator and with the optimal colorimeter receiver. So we can do it for the demodulator, and it's easy. We just use the received signal multiplied with the carrier signal and do the integration. And in the digital case, they will need to do the integral, and will be multiplied with the RTX. Optimal colorimeter. This will be the BXK. And the matrix form. And and we can do it so the detection with compared with some threshold for BSK, which is the hub energy. And for the 2 and 3, we have the S1 multiplied with the received matrix 2 and greater than the other frequency S2. So will be the frequency later, and for the 0 is the and the threshold will change to 0. Now we have to check the errors and estimate the error probability. So, which is the number of the error. Just sum the e equal of the detect the symbols with the binary symbols. EEM which equal to error number of the errors. And for the BER estimation, we can use our specific BER and compared with the total of the numbers, which is we have the number of the bit rate with 10,000, and we use the errors divided by the total numbers. Then we can get the error rate. And in each k with the k index, not only the one. Here we have to use it. We think it be a value with the k, and use the errors divided by the total transmitted data. Divided by n. That will be the BER value estimation. Estimation. And we just use some function to separate print. And this is for the BXK. So noise ratio will be also, and for the f divided by n, and we white the single noise ratio here is according to the index with the k, and the BER value also index. And the step of this step is the for the BXK case, and let's do it for the frequency shift key. Here we just like 2. and 2K. Read with the so this will be the BFSK. And the value will be the 2. And for the sum of the 3 and the arrows will be the 3 where you arrows, and here their value is sum of the arrows is 3 base 3. So that's all, and we can see now we have to plot it. With the synchronized ratio and with value with the red and crypto stable and R B labor there, and we hold on. So uh just change the value and the different color synchronous ratio there, and what else? 3 green in color, and we give them the legend. So first is the BSK, second is BFSK, third is the BPSK. So it seems everything is done here, and uh, that's right. Now it will look okay. It's a mistake here, 57. Ooh. We used a different key. Okay. Undefined as 57. Here. Okay. Yes, you will see here. with the step with the 0 to the 0.5 to the 1 and keep going with step with the 0.1, and it's quite faster. I only have the transmit data with the 10,000, and in your case you have to transmit the 1 minute data. And you will see the BER from the increase, the signal to noise ratio increase, and BER will decrease. So for the maximum is the 15, and it will reach very quickly. Yes, and this is use the plot method, and you will see, well, it's really hard to read it, and we have to change the plot method. This is BSK, and this is BFXK, and well, hard to understand what's the difference. And here we have to use the change the plot as another expression function is the semilog, which will just plot with the log result, logarithm result. Let's run it again. Costs some time, but it's okay, not very slowly. Huh? It seems the frequency shift key has some problem, and you will see here it decrease very fast. Let me check it. The frequency shift key has some problem with frequency 2. Yes, frequency shift key has the noise ratio here. 3. Number of error divided by the 2. For the shape is S1, S2, matrix S2. This is correct. Plus the noise. And for the random, it is the 2 divided by is the S1. Two is the 2 pi multiplied with here. Is the grounding application true? Ah, here I use the different same frequency. I have to use the different frequency here, so it will be same. Let's check will any mistake here. I think F1, F2, F1, F2. No, nothing more. Let's try it again. USC frequency has okay with the different value. Yeah, now it has different value. Let's see, it's just some wording, but it works. Yes, yes, it has, but I just hold on and sorry, let's find it again. So it will each time it will record the previous day result and just hold on. Yes, so it will look like this, and you will see the uh, frequency shift key has phase shift key has the best performance, and in the here in the different signal noise ratio, and it already can reach to the 0. However, in for the amplitude and the frequency for the amplitude shift key, you will see here still has some left noise, and for here, and why here it's just stop here because the result is already 0. So when we just use the logarithm, we plot the logarithm, and we can get nothing and just maintain 0. And instead means it still has the noise stay here. It's not noise stay here. It's just a zero value, which means the 0 mistake. But if you see the amplitude shift key, you can see it still left some small errors here, and for the frequency shift key and the phase shift key, there is no error, and BER is 0, 0, 0, 0. So and in here we have to do some comparison, like this task, the next step, we have to do for the on-code simulation mark, and it has some theoretical value calculated in the task 4B. we use the specific bit error rate, and we use the specific signal noise ratio then, and combined with our three different modulation tab and calculated the serial optical bit rate error point. So, and we compare with the our BER curve. So let's do it. And I just start here, and it will. We need to calculate the error, so we have to use this function. We already task 4b, which is the we have to use the error probability of the three modulation types, and we use this function, EIF function, in our case. So we do it. And firstly, we already know the specific the single noise ratio value. We can calculate the energy of the signal EB with the noise power, spectrum power, and with the specific different value. And we will not use the dot. We just use the because it's the single value. We just use this square. Here is the signal noise value divided by 10, and there is the for the here we can score it without the x. We can calculate the x here. So for the amplitude shift key is squared. Just by the 2. This is for the xk, and for the fxk 2. And we have the we just is self. Yes, here for the frequency just itself. And here we need to multiply it with the 2. For the see for frequency shift gain and phase shift gain, we just multiply 2. And next we calculate the error probability. So the error 1 minus this function, function. We have the multiplication 1/2, 1 over 2, multiplied with 1 plus f divided by s squared with the divide by the s squared 2, and it will not change the for both for all of them, and will be the error for BSK. Now we need 3 periodic value. This is the second, third, and for the just a change here x2, x3. and error probability for the, let's say, shift key and base. Uh, uh, and we have to uh, just plot plot it, and we still use the uh, with the uh, value, the theoretical probability error. Here for the frequency, 2 and no 3. We change the color is the and and give it legend. With give it as a legend with the theoretical value like TV theoretical value BSK and for the frequency and we have to hold on even we don't hold. So I think there is no mistake. This is a plot and this is theoretic point and we write. So, and for here, I would like to mention about you will see for the 12 for single noise value, single noise ratio value, and it has some theoretical uh, error probability. And you will see here is highest for the BASK and second for the BFSK is better than the BSK and the best performance is the uh, BPSK. However, in our case, real case, you will see here the both of the frequency shift key and the phase shift key already the pair is already 0. So which means our theoretical case is already better than our no, our real case is already better than the theoretical uh, error errors, and we can see the plot. And as I already mentioned about you will see here for the plot, we use the plot, and if for the BER, the errors is 0, and after plot this is nothing, will not keep going, and we will not plot, and it will not show more. However, you will see here, and the BPSK periodic value is here, which means it's already 0 here, so it not show here. So, and for the BFSK, you will see here, basically it's close to here, and our real case, it has a little bit better than the theoretical case. And for the binary amplitude shifting, you will see here, basically it's same, right? And if you have more case, if you have longer sync noise ratio, if you have more data, if you have a smaller step, and you will get the better matched plot, which like this. However, in your case, you only need to choose one of you only have the one. You need to choose one modulation tab, and make your here you make your analysis and make your conclusion on use the code efficiency. And today we already finished the first subtask without having code there. And the next course, next week we will finish this course, and we will keep going for the second subtask, and we will do some error correction, which means we have the encoding metrics and the decoding metrics we will add in before the transmit and after transmit. So it will not very difficult, and if you don't understand the sixth step, the first subtask, you can ask me or Dr. Enes, and if you have any questions, and please, I think if you pay more time, if you spend more time on studies, and it will not be very difficult. So today, thank you for your attending, and see you next week. Thank you, everybody, and goodbye.
Thank you. Bye.
Thank you.